Internet, John McDonnell here, and today I'm going to be testing out some newly acquired tools. The first being a Kingst LA5016 model, which is a 16-channel logic analyzer, which has 2 additional pulse width modulation channels. In order to test that, I'm going to do some functional analysis utilizing the tool and analyzing a Arduino R3 analogWrite method. This here is the tool I will use to do the functional analysis of the Arduino. As you can see, it has a 500 megahertz max sampling rate, 16 input channels, and a negative 50 to 50 volt range. This does require the use of desktop software as well, and it also comes with a variety of extras, some extra cables and alligator probes for doing your analyzing. In order to use it, you have to install the software on your computer, and that's about the only downside, even though I don't really consider it a downside, considering logic analyzers and a lot of electronic test equipment can range upwards of $5,000, $10,000, $15,000, and this is a great learning tool that actually I think is functional too, and can do pretty decent logical analysis on things like CAN systems and things that are in the negative 50 to 50 volt range. The software, the only downside of it is it's more of a still frame real-time analysis. It's not a actual live monitoring. It does a repeated frame capturing, so that is, it works. It's not bad. You get a decent analysis, and it will help troubleshoot and debug signals and such. And then in order to demonstrate it, I'm just going to do very basic introductory analysis of the Arduino, which I showed you there, which is the R3 board, which I have sitting right here. I'll show this to you. And in order to do this, I just have 2 basic wires, which I'm going to plug into 2 of the Arduino pins. Now I'll explain why that is here in a second. But here is the Arduino board. Okay, and I just have this sitting on my desktop, right? Plugged into USB, and it's important that it's connected to your computer as you do this. So the very first thing I'm going to do is take, these 2 wires here, okay, and I'm going to test this out because the Arduino analogWrite function, especially for the R3, and I'll post this as well in the video. It's depending on your board, the pulse width modular pins, the pins that are capable of handling pulse width modulation are enumerated on the specification. So for the R3 and earlier, for instance, PWM pins are 3, 5, 6, 9, 10, and 11. And the reason why I have 2 wires here is I'm going to just, demonstrate the differences between pins 5, we'll say pin 6 and pin 3. Okay, pin 3 runs at 490 megahertz, and pins 5 and 6 have a faster frequency of 980 hertz. And this will kind of help differentiate the different channels on the logic analyzer and kind of show you the cool thing about this in terms of organizational labeling and correspondence to your code, which correlates to your hardware. So the very first thing I'm going to do, and I'm going to grab the camera here and kind of just go along and show as I do this, so it's easy. And sorry about the motion here, guys, but here's that. And simply, if you look, and again, I apologize here, but if you look, let's get this not blurry. You can see the pins are labeled there on the side, right there. So what I'm going to do is simply plug my wire here into pin 6, as so. And I'm going to take my other wire and plug it into pin 3, as so. careful because it starts at 0. Okay, so we have that plugged in there. And we have that one plugged in there. Okay. So there's those. And for the moment, what I am going to do is set this right here. Bring over my logic analyzer. Okay. I'm going to plug that in as well. You can hear it fire up. And basically, you just need to connect one of your probes to your channel wires here. Okay. And since we're going to analyze 2 channels, basically each one of these wires, we just got to take the alligator clip here, connect it onto our pin 3 of our Arduino. We need to grab another one of these probe clips, and this is kind of the weird thing I found with these is these pins, these probe clips here, are not quite like the original predecessors where they had a hole in the back here and you can just take and plug your pin directly into it. It actually, as you can see, has the pins on both sides. And it takes a little finessing to get these to sit in there right and stay. I didn't really like this, to be honest with you. Although it works, and once they're on there, they tend to stay on there. But I kind of find it a little tricky to get it on there, and because they go on, you know, in pretty simple ways, and it feels like it's on, but it's not quite secured on there. Okay, and so once you get it, you know, it's kind of like a shark bite for you plumbers out there. If you've ever dealt with those, it's like, oh, it might feel like it's on there, but if you don't feel it like seat all the way, it won't stay. So that is really the only complaint I have about this thing so far. It's really not even that bad of a complaint. I could probably buy the original alligator clips. So we're going to clip that one onto our Arduino pin 6. Going to make sure that my cable's in there. And we're all set up to capture some signals. Okay, so you can see. And this is where I'm going to switch over and bring up a live video feed of what I'm doing on the computer, because that's pretty much all you need to see at this point. And in order to follow along with this, you do need to have the Arduino IDE. And in this case, I'm using 2.3.2. And I've gone ahead already and pretty much on this computer, you know, just plugged in the USB. It found it, and then the Arduino dropped on it, selected Uno on COM5, and it was ready to go. You'll also need to fire up and install the CD that comes with your logic analyzer on your computer in order to capture your input onto your computer. So now here we're in Arduino, and as you can see, my Uno has been found and detected on COM3. It was pretty basic USB setup. And the first thing I'm going to do is just quickly define some standard variables for our pins, which I'm going to uncreatively name them PWM pin 3 and set that to the integer 3. And do the same with our pin 6. Okay. And as you remember in the function prototype or the definition of the analogWrite method, pin 6 runs at 980 hertz. So I'm just going to throw some comments in here. And pin 3 runs at 490. Hertz. Okay. So I'm not going to make this overly complicated, so we just have to throw in our setup function and, you know, set our pin modes for the pins we've just defined, because we're going to send them outputs, right? We're going to send a pulse width signal to it, basically analogWrite, and we're going to write some output to it. So just quickly copy and paste that and change that to pin 6. It's the same thing, okay? Save it, go down here, write our loop, okay. And then I'm just going to go ahead and write the analogWrite function in there. And we're going to send it, well, we're going to write to pin 3 a pulse width, okay, for that there, we're going to. And now, according to the functional prototype, we need to define the pin we're going to write PWM to, and the second input parameter is the duty cycle, okay. So here is the duty cycle, okay. And according to the functional prototype, this can take a value between 0 and 255 or 256 potential values, with 0 being totally off, meaning with pulse width modulation, it's basically a discrete on-off. Okay, so if you set it as 0, our signal is just going to stay off, okay, like so. Now, half of 256 is 128, so that is half. That gives us a 50% duty cycle, and that's what I'm going to set pin 3 at. So I'm going to set that at 128. And in the comments, I'm also going to indicate that, so 50% duty cycle. All right, meaning for every off, we are going to have an on function. Off, on, off, on, off, on. Okay. Now, I mean, they should actually be the same width size here. And that's an interesting point to show you. So, pulse width is this. So here is your pulse, okay, and then your on. Well, if I could, let's see here, get an upper one. But anyways, the width, so this is off, that's on, that's off. This is the width of the value you're sending in that pulse. That is the width of that particular pulse, and that usually represents a voltage or some other type of value that you're sending to some sort of instrumentation, like in most cases with Arduino on-off blinking LED. More advanced cases, in the Arduino's case, you can use it to control a motor, and pulse width modulation goes well beyond Arduino and gets into advanced cases like space vector pulse width modulation, which is used in more advanced motor control and things that you see, such as factory automation, electric vehicles, all kinds of things like that. And it gets pretty complicated in terms of the underlying theory that drives space vector modulation, and it's actually part of a component of motor control that is called field-oriented control, in which you're controlling it through the field, the electric field of the motor, instead of doing 6 predefined motor steps in a sense. But that aside, I'm going to keep this at a simpler node, so I'm just going to quickly copy and paste that. Change this to our pin 6, which, as you noticed, we had set up in the beginning there. We clipped our probes to. And for that, I'm just going to cut this in half again to 64, which is going to give us a 25% duty cycle. So, and that is at 980 hertz, and that is at 490 hertz. So, when we run the digital logic analyzer, okay, pin 3, all right, which is connected to our first Kingst Digital Logic Analyzer channel, or the purple channel. So pin 3 is purple. Now guys, this might sound kind of weird, but I want you to remember that. So pin 3 is purple, okay? And then this pin here is blue, or our logic analyzer, channel 1. And here is our logic analyzer channel 2. And that is just arbitrarily based on how I connected them, right? So I could swap those around. There's no rhyme or reason to it. It's just how they're plugged in, right? However, that does correlate to the software that Kingst provides, okay? And that's actually what I'm going to show you next. So I'm going to save this, and I'm going to upload it to the Arduino. Yep, totally forgot to put some semicolons in there. Sorry, guys. All right, got busy talking. So save it, upload it, uploading complete, and yes, the read write. Okay, so we're good. Now I'm going to switch over to the Kingst Logic Analyzer. All right, here we are in the Kingst VIS application, and as you can see in the bottom left here, it says our device is connected. It was found pretty easily. It's just standard USB. Plug the analyzer in, pretty much finds it. You use this function up here. You can select between your different models, and as you can see, the LA1010, LA2016, the 5016, and the 5032, and this here, the difference between the 32 and the 16 is just simply the amount of channels, and I felt that the 16 channel was more than enough that I would need for this. Currently, I just wanted to have the max frequency, so there we have that. And as you can see, on the left hand side we have our illustration of channels, and as I showed in the code comments, and matching the actual wires, they are color coded, which is pretty cool in order to keep this organizational flow from here to our code to our actual logic analyzer. And we could even go further and keep our wiring, our buses, and all sorts of things color coded that way if we wanted to. So, for instance, here indicating channel 1, okay, the purple probe wire, or channel 1, is connected to pin 3. So we just simply label this what we labeled our variable for pin 3 in the Arduino code. So PWM pin 3. And the same for channel 2. You know, so we go PWM and 6, and there we go. Now if we connected everything, did everything right, wrote our code right, uploaded the flash the software to it, running this here should give us a pulse width modulation signal on this channel and this channel, representing each pin. What I was talking about earlier about the only slight disadvantage of this program, which is really not bad, again, is it's a still frame capture, like a recursive loop that does still frame capturing. It's not a full live monitoring like you would have on something like your oscilloscope or more expensive analyzers, right? So you could take one still frame, single sample, or you could take auto sampling, which I'm going to go ahead and do now. And as you can see, our auto sampling is working, and we have our signals showing up for our channels. So everything seems to be working pretty good. It shows us our duty cycle over here on the measurements. And I'm going to stop the sampling real quick, zoom in here, and just kind of give you a quick explanation. Again, this is what a pulse width is. You know, you have your rising clock edge and your negative clock edge, or your positive clock edge here, which is going up, it's positive, and then you have your pulse, which is, this. And the width of the pulse is what is being sent in this signal. So it is literally a pulse width that is sent. And depending on what that is, what this off,
on represents, usually in this case, 3.3 volts, okay, is being sent with each pulse. You can do a variety of things, such as most commonly used in Arduinos is to blink a LED and motor control. You can send pulse PWM for motor control. You get into more advanced PWM techniques, such as field-oriented motor control using space vector pulse width modulation, which is a more advanced version of it that I encourage you to look at. And I'll do a video on later. Companies out here in Michigan, a lot of engineering and automotive companies are doing that as sort of a standard outside the generic, 6-factor motor control. Companies like Infineon, for instance, have great tools that go ahead and allow you to test that. And this is a great way to kind of analyze. You could use your digital analyzer here, to check out how that works and see those signals and see how the variety of techniques and controlling motors works and get an actual visual of it, right? So, and what I was talking about before, and now we're analyzing the function of the Arduino, the actual analogWrite function to test out its functional prototype parameters or arguments, right? As you can see here, the gray line indicates one wavelength or one cycle of the pulse, right? And so we set our first pin to 128 out of those 256 potential values, which I noted should indicate that we have a duty cycle of 50%, which if you look over on your measurements here, you can see the duty cycle is represented at 50% approximately. It's also correctly giving us the proper frequency, which I did state as megahertz earlier in the video, so I do correct myself on it's 490 hertz. However, it's still showing correctly, so everything's working as should with the function, as should with the hardware, and we're confirming it. So we look at our second channel and our second pin, and we can see that it is in fact only giving us a pulse width of at a 25% duty cycle here at a frequency of 970 hertz, or almost the 980 hertz that the function allowed it to be for that pin output. Okay, so there really isn't much more. Obviously, you could go ahead and continue to hook up and test a variety of different things on each of your channels, adjusting the different duty cycles and testing out the different pins and trying a variety of things on your channels to test out and see how your Arduino is really working and get a good visual representation of it. And what's very cool about this is, like, if you're in any kind of advanced electronics or electronic study, these things are one of the best ways to draw a state diagram, in my opinion, quickly, if you ever need to do such a thing, because you get all these different channels and you can analyze your circuits and you connect your different channels up to different parts of your circuits to get your various operational states. And you get into the further state diagram calculations and such, and these are one of the most helpful tools you can have for that. Or even if they're virtual, software based, and things like Simulink or LabVIEW or any of the other multi-sim programs that you're using for circuit analysis. So anyways, that's pretty much it. I'll get into more advanced stuff later on as we go along, things such as using an oscilloscope and some low voltage, I hate to say low voltage, but like voice data video kind of things, just regular general residential electric, variable frequency drives with low pass filters, and analyzing with the low pass filter and multimeter. That's one of the cool things I plan on doing. Also getting into some more complicated circuit builds, I should say, in terms of actually, taking and testing out electrical properties that we all just kind of use and take for granted. For instance, true RMS on our multimeters, going through and actually deriving where our basic formula calculations come from in terms of doing like peak voltage times 0.70, just to get that number nice and neat for us. We're going to actually go through the integral derivative. We're actually going to integrate, and we're going to derive that number using integration. Okay. Not only that, we're not going to just do the mathematical calculations, but we're going to try to do it in hardware. Just recreate a way where we can actually calculate root mean squared in a circuit, in code, analyze it. That way we get a full understanding of how this is done inside the hardware of our multimeter, for instance. So a lot of other cool things like that. Solving a lot of different equations using circuits and stuff like that too. So anyways, have a good one and stay tuned.